Hi everyone, my name is Diogo Ribeiro. I'm a student, a PhD student at Université Laval, and I'm going to talk about metal mobility in metasedimentary belts in the Superior Province and what are the implications for gold endowment. So different sources have been proposed for orogenic gold deposits, and it's generally accepted that the most important fluids involved in this kind of deposits are metamorphic fluids generated by the devolatilization of supercoastal rocks. So as we increase pressure and temperature, we're going to break down hydrous phases and form a fluid phase. And the devolatilization model predicts that at the transition from green schist to amphibolite phases, we're going to produce significant amounts of fluid and release it at that boundary, usually when chloride tends to break down. Tompkins in 2010 did predict that also at the similar conditions, PT conditions, then the temperature-dependent chloride-out reaction, we would have the pyrite breakdown. So in this situation, we will release fluid, sulfur, and if that pyrite bears gold, we would also release gold at the same time. In the Phanerozoic, the metasedimentary rocks are generally accepted as a suitable source for this kind of deposits, as it's been shown by Pitcairn in several studies. But in the Archean, they've been mostly disregarded because of their low abundance in greenstone belts. However, in the Superior Province, we do have thick metasedimentary belts that are adjacent to the endowed greenstone belts. They are much more metamorphosed, so devolatilized. There was a lot of fluid extracted from these rocks, and given this tectonometamorphic setting, it's fair to admit that they may have sourced metals, fluid, ligands to the adjacent orogenic gold deposits. So that's what we're trying to test. It has been started by Pitcairn and others in 2021. They did collect metasedimentary rocks in Rouyn-Noranda and Val d'Or across different metamorphic grades, zones, and they did ultra-low detection limit analysis for gold and other trace elements. And what they found out is that there's a systematic depletion of gold, arsenic, and antimony with increasing metamorphic grade, which means that these elements are mobilized during prograde metamorphism. However, there are some things missing, like the constraint of PT conditions. What are the key metamorphic reactions controlling the release of these elements? And tracking element mobility at the mineral scale. So that's what we're trying to do in this project. We're working in the Quérico and Pontiac-Sous provinces, and we're assessing whether these metasedimentary packages were a suitable source for metals, ligands, and fluid. So I specifically will track the mobility of these elements during prograde metamorphism, and to do that I used whole rock geochemistry and ultra-low detection limit analysis for golds, couple that with in situ analysis in prograde metamorphic minerals, in this case sulfides, and we're going to conjugate that with the information coming from Adrian's and Isaac's project on the PT constraints of these rocks. And the ultimate goal is to get the optimal PT conditions for the release of gold-bearing fluids from this kind of rocks. So specifically on my project, I'm working in these two belts in 3 different areas with contrasting gold endowment. The gold endowment is based on the amount of gold occurrences nearby. So we have Rouyn-Noranda, which is the well-endowed area, just south from the Abitibi gold camp. We have Geraldton, south from the Beermore-Geraldton belt, and Thunder Bay, where there are no gold occurrences around, which is the poorly endowed sector. Geraldton is the moderately endowed. So I went to the fields, I sampled all the prothelites I could find, tried to get also spatial representativity, and I sampled across all metamorphic zones. This is an example from Geraldton. I did the same for the other 2 areas. And basically I have a suite of mainly metasedimentary rocks and some subordinate mafic volcanic rocks. I will focus on the metasediments. So I selected some also for whole rock geochemistry, and I'm going to show you that right now. This is the data for arsenic and antimony for the 3 areas, and what we can see is that in low-grade rocks, the 3 areas have identical concentrations. The metasets from these areas have identical concentrations, and there is a systematic trend for depletion in these elements with increasing metamorphic grade downwards. However, when we look at gold, what we see is that even though there's a systematic depletion, even though they have the same gold concentrations at low grade, and there's a systematic depletion of gold with increasing metamorphic grade in endowed areas, we don't see the same for Thunder Bay. So for some reason, gold was not efficiently mobilized in this area. And in order to understand that, we have to look at the mineralogy. This is usually the general mineralogy of a low-grade metasedimentary rock. And we did some tests, and as we expected, gold is hosted in sulfides. So we need to track their changes, their textural changes and chemical changes throughout prograde metamorphism in order to understand why these areas are different. So in a general way, there are 2 main reactions that are visible in all the 3 areas. In the first one, we start with the pyrite 1, which usually has subhedral cores. They are inclusion poor, with anhedral rims. They are inclusion rich. And with increasing metamorphic grade, these tend to transition to pyritites, usually featuring these intermediate sulfide phases, displaying a linear fabric, and they mark that transition from pyrite 1 to pyrite. At higher grades, we start having a second generation of pyrite, which grows inside pyrite and eventually consumes it completely. So these are the 2 main reactions. When we compare the 3 areas, so we have here pyrite 1, pyrite and pyrite 2, we can see that Thunder Bay is definitely different. And how? So basically, pyrite 1 is generally much more abundant, especially at higher grades. So we find much more pyrite 1 at higher grades in Thunder Bay than in the other 2 areas. The other thing is that we don't see, it's rare to find the textures that I showed you before, the ones intermediate between pyrite 1 and pyrite. Usually what we see is a broken pyrite 1 sealed by pyrite. And also a generalized low abundance of pyrite. So this is due to the fact that pyrite 1 does not break down efficiently, but also because pyrite 2 grows quite early. This means that pyrite has a limited field stability in this area. In Juanoranda, we do see an early growth of pyrite 2 too, but the pyrite 1 to pyrite transition is much more abrupt and efficient. As we can see here, by the biotite zone in Juanoranda, we have model proportions of pyrite 1 that are far less high than in the other 2 areas, and eventually it breaks down. In Geraldton, even though the breakdown was efficient, it's very progressive in the beginning, but eventually it does break down. However, in Thunder Bay, as you can see here, from chlorite to garnet, there's a decrease of model proportions of pyrite 1, but then it stabilizes. So that's that. So now let's look at the trace elements in the sulfides. We'll start with Juanoranda, and we have in yellow pyrite 1, pyrite in brown, and pyrite 2 in blue. So what we can see here is that pyrite 1 is the main host of arsenic, gold, and antimony, and this is the same for all the 3 areas. It's the main host. And we can see also a trend for decreasing of these elements in pyrite 1 with increasing metamorphic grade. Then we compare it with pyrite, much lower concentrations. Gold is not even above detection limit most of the time. And also for pyrite 2, gold is much lower, usually not surpassing 40 ppb. When we look at Geraldton, same thing, same trend. decreasing of the concentration on these elements with increasing metamorphic grade. We'll look at pyrrhotite, lower concentrations. Most of the gold analyses are not above detection limit. And pyrite 2, same thing, quite low gold. But then we look at Thunder Bay. And what we see is that even though there's a decrease of arsenic and antimony with increasing metamorphic grade, for gold it's basically stable. So gold is not being efficiently released from pyrite 1. And also the one that is released, it's also being stored in pyrrhotite, for example. We have much higher concentrations in gold in pyrrhotite in this area, and also in pyrite 2, higher gold content. So the gold is definitely not being efficiently mobilized in this area. So we did track the mobility of these elements at the basin scale and the mineral scale. We compared different transects with contrasting gold endowments, and what we know is that even though they have identical concentrations at lower grades, gold is not efficiently mobilized in Thunder Bay. And also we know that pyrite 1 is the main host of arsenic, gold, and antimony, that there are two main reactions, first pyrite 1 to pyrrhotite, and then pyrrhotite to pyrite 2 at higher grades. Pyrite 1 to pyrrhotite transition is the main reaction controlling the release of these elements. And we know also that the reason why gold was not liberated in Thunder Bay was because there was the breakdown of pyrite 1 was inefficient. So gold release was precluded. So this means that there is a multi-scale spatial correlation between gold mobility in metasedimentary belts and gold endowment in the adjacent segments of the greenstone belts. So these are the main conclusions, and now I'm just going to show you a bit the ongoing work. So I did perform whole rock sulfur isotopes in order to try to establish tracers and try to find a link between the potential source and the sink. What we see here, it's very confusing, but what we can see is that even though we sampled across, we're doing this analysis across 3 basins that are quite big, we have limited variation in terms of cap 33 and delta 34S, and there's no correlation with metamorphic grade. This means that metamorphism has no impact on these signatures, which means also that cap 33 may be a robust tracer, as usually is used for. So I tried to separate the different samples by area and also giving them different shapes according to the main sulfide in each rock. So either pyrite 1, pyrrhotite, or pyrite 2. And I mean, there is kind of a trend for lower cap 33 in the samples dominated by pyrite 1, and then it increases for here in the squares dominated by pyrrhotite, and the triangles tend to be have higher cap 33 signatures. But we still don't know what that means. We're still working on it. But what we can say is that these samples do follow the Archean array, so the dashed line, which means that the sulfur in these sulfides, the precipitation of these sulfides, the sulfur is coming actually from Archean seawater. It's not actually magmatic or coming from a VMS, for example. And then looking specifically at Juan Oranda, because we have data from Michael Herzog in Val d'Or for cap 33 in orogenic gold deposits from Val d'Or. We tried to basically compare our data with his, and what we can see is that the data from cap 33 from Juan Oranda does not match the ones that Michael got for Val d'Or, but they do match Canadian Malartic, which is hosted in the Pontiac sediments. And basically this means that the Pontiac sediments were probably not a source of sulfur. And if this is the same for the other areas, this means that this may mean, we still don't know, but the metasedimentary belts, even though they may have been a source for arsenic, gold, and antimony, they're probably not a source of sulfur. Sulfur may be locally sourced at the sink. Thank you.